Hi, my name is Tom Verbeure and I'll be talking about hacking a 30-year-old oscilloscope. This all started when I wanted to add support for Tektronix oscilloscope to a tool called GL Scope Client. It's a tool that allows you to post-process data acquired by oscilloscopes on your PC. Now, I didn't have a Tektronix oscilloscope, but I was able to find one on eBay for $160. So I bought that one, and when it arrived home, it worked. Now, one of the things I had to check first was whether it or not had issues with leaky capacitors. An interesting thing is that in the early 90s, there was a lot of capacitors produced that were actually broken. And after a couple of years, like 5–10 years, the electrolytics would start leaking out of it and corrode the board. And this is still an issue when you buy electronics from that era. For example, all the Macintoshes and stuff, very often you will have to replace these capacitors, otherwise they won't work. But mine was okay, it was produced in 1996, so there was no issue anymore. Now, oscilloscopes these days, and back then already too, they come typically with a bare bones functionality, and then you pay extra money for additional options. In my case, the basic options were a port to control printers of that day and a floppy drive, not very interesting. There were three other options that the scope supports. One is the video trigger interface for PAL and NTSC, which is now obsolete as well. There is the advanced DSP option, which allows you to do stuff like FFTs on the incoming signals. But most important, there is the option to have a sample buffer of 120,000 samples instead of the standard of 30,000 samples. So here you can see what those two first options can do, the video and the DSP. It's basically a software option, so I didn't expect there to be major issues with that. But for the 120,000 options, you need enough RAM. So the first thing I did was count, is there enough RAM on the board? And it turns out, yes, there are basically 16 32 kilobyte RAMs. That's basically 128 kilobytes per channel. And so I thought, okay, well, this looks good. All I need to find now is how to enable that function. Well, the first step to get there is you need to extract the firmware. And this is a process that's relatively well documented on the web. It requires switching some toggle inside the oscilloscope with a little screwdriver. And then with a GPIB interface, it's an interface that's used in the 90s and earlier for almost all test and measurement equipment. You can basically read out the firmware. And so once you have that, you can use the strings command in Unix to check, well, is there anything interesting in there? And one of those things is, the VxWorks logo. VxWorks is the operating system. It's currently still used for automotive, medical equipment, robotics. It's even on the Mars 2020 lander. It's very good for embedded systems, has lots of real-time features. Another thing that I found is a whole menu for commands, and that's a good thing because it means there is a console in there somewhere, a debug console, that will probably help me executing commands and figuring how things work. And then most important, there is a functions symbol table, and that's really the holy grail of reverse engineering because it allows you to annotate binary code and figure out what the code is doing without having to guess. So the next step is getting a serial debug console up and running. So you basically have to remove the casing of the oscilloscope, and then there is another RS-232 interface. And I was hoping that I could use the same internal cable that was also used for the printer. Well, it turns out that in all their wisdom, Tektronix used a different pin assignment. In fact, the pin assignment was 180 degrees different than what I need. So I had to rig up something myself, but eventually I was able to get that to work as well. And so then when you boot up the scope, you see all the boot up messages and everything was looking fine. And finally you get a command line. And what I figured out is that the symbol table is included because all the symbols that are in there can not only be called by regular C functions, but you can also type them on the command line. VxWorks supports that. And so there is a separate process running in the operating system, and it takes in these commands and just executes them. For example, you have the ring bell function, and if you type ring bell on the command line, you have a bell going on. So the next step then was to look at what the code was actually really doing. And for that, I used a tool called Ghidra. It's an open source tool created by the National Security Administrations of all people. And it allows you to read in a binary image and a symbol table, and it will then reverse engineer the assembler code back into C code. It supports all the popular CPUs from today and also from the past, including the Motorola 6802 that is used in this oscilloscope. So for example, here you see the ring bell function. It's obviously very simple. It checks, first of all, is the bell enabled in software? And if so, then when you want to ring the bell, you need to write a value of 10 hex to the register port A, and the bell will ring. And this is really very useful to quickly determine, how hardware is working. Now, you don't really always need a symbol table. For example, the boot ROM does not have a symbol table, yet it prints out a lot of diagnostic messages, and those are fantastic pointers to figure out what certain code is doing. For example, in the code here below, you can see that it's printing out GPIB test passed. Well, from that you can figure out that the code before that must be testing the GPIB. And so then you can, in Ghidra, annotate these functions with a nondescript name, with a descript name. And as you do that, eventually you can figure out what the whole code is doing if you just spend enough time on it. It's like a game of following breadcrumbs in the forest. Now, so it turned out that one of the most important features or functions is the hardware accountant query function. In a Tektronix oscilloscope, there are 16-bit feature numbers, and so every hardware feature has this unique number. And I could figure out that there's a whole bunch of them, including the 3 that I was looking for. You have one function, the 2B8, and that returns 30,000. That's basically the 30,000 points that is currently supported in the oscilloscope. Then 317 is the math pack, that's the DSP function that I'm looking for. And 700 hex is hardware probe TV trig present. So let's look into one of those. Hardware TV trig present turns out to be very simple. All it does, it reads from a fixed location in non-volatile flash memory. And when that location is 1, then it says, okay, now that feature is enabled. And the same thing was true for the math function. So one of the other functions is libmanager word at put, which writes into the non-volatile flash. And so on the console, I could simply give the 2 commands to set these values to 1, and you reboot the scope. And wouldn't you know it, suddenly those 2 features are enabled. It was really that simple. And so you can see on the left, indeed, there is now the video trigger menu enabled. And on the right, you can see the FFT of a square waveform. Now, for the 120,000 samples options, things were not that easy, because there the feature check not only checked whether that particular non-volatile memory location was set to 1, but it also had a function that actually checked if a certain memory was big enough. And that function failed, which is weird because I thought there were enough RAMs, but it gave me a clue that maybe I was looking in the wrong place. And indeed, there it turns out to be another plugin board in that oscilloscope on which there were 6 RAMs missing. And so that's the reason why the function didn't work. Now, these RAMs are very old, of course. They're not in production anymore. But there are these second-hand brokers in China that will basically sell refurbished RAMs. And so I ordered 6 of these RAMs, soldered them on the board, set the non-volatile function to 1, and upon the next boot, the 1M function, which is the 120K option, it worked. So basically, I had a total success. All the options that were disabled were now working. Now, I want to spend one final minute on Smalltalk. Smalltalk is one of the first object-oriented languages. And it was really quite, people were hoping it would become possible somewhere in the 80s, and Tektronix was really betting on that. In fact, they had quite an extensive line of AI workstations that were running on Smalltalk. Now, this thing clearly didn't really go anywhere, and eventually the Smalltalk infrastructure moved to their oscilloscopes and other test and measurement equipment, including this particular scope. Now, unfortunately, there's almost no information to be found. I mean, there are some hints that the floppy disk could be used to install extensions to the scope that might be Smalltalk based, but I really can't find anything about it, and that's really a pity. Tektronix basically eventually started to phase out Smalltalk, and by the end of the 90s, all their new equipment was using Windows, and that was the end of the Smalltalk story. You can find much more information about all of this on my blog. I have an extensive 5 blog post series about this whole reverse engineering effort. There's also some info on Oscilloscope client, and you can follow me on Twitter. And thank you very much.